Okay, we will before ending of our today's class, we still have about a few minutes left. I should stop 5 minutes before our start talk. Then if you have anything else, mark out first. Then later we discuss. Maybe 10 minutes. Okay. So last week we already go through a lot about this different type of index. Chapter 7 is regarding index, and we know for a lot of the database, the searching is actually more frequent. Okay, more frequent than actually do the update and the deleting. Yes, insert of course. Yes, daily of course, daily transaction is actually doing the insertion part, insert all the record. But I think the most based on the business type of a business, actually this searching is quite a lot. So when you browse at Lazada, when you browse Taobao, or even when you go to this e-banking, a lot of these transactions is actually browse first. You check your balance, and then you check your credit limit. It's actually go through searching rather than doing the updating, or only when you withdraw, if you check your balance is enough for you to do the withdrawing, and then you withdraw. A lot of times during a month end, I want to go log in and do some payment. Let's say my child this tuition fee. Oh, eventually there's not enough money. So I search, I get the balance, then I just log off. So I do nothing, but I just searching, see what is the balance. If I got money, then I do the payment. If no, after searching, I just log off. So that's why I say a lot of these transactions for this activity is actually a searching. So for last week until now, we have a lot of this different kind of index, and we know index is very important. If your searching is using a 1 second compared to others, means multiply by a billion of a transaction or activity, means your transaction, your computer will need thousands or millions of times compared to all others. Okay, so that's why we come up with a lot of different kind of index. And today we'll go through this B plus minus 3. We have if we go through this like programming, this one is really interesting. But if for database, we actually do not need to go to that this, but we just need to know actually what is this regarding. Okay, so a B3 must satisfy the following of property. All the type from the root here. This one is the root to the list. This one if without any of any of other nodes connected to the branded here, then we can say that this one is the list node. So this one is non-list node because we have the root. It also have list at the back here. So this one non-list node, and this one is the list node. So all the path from the top to the end should be the same. So this one is 1 level, 2 level, 3 level. So if the path here is 3 levels, so all the nodes here it should be only at 3 level. It won't be accidentally come another one that is 4 level. Okay. So if we want, if these 3 do not have enough space or node to connect, then it will restructure and become a 4 level. Okay. So this one is the static. Each node that is not a root or list, sorry. Sorry, the internet line suddenly disconnected. Okay, so we already mentioned here we have the root here, then we have a non-list node, and the final part is the list. So it means for each of this level, it should be fixed. Okay, it should be fixed. So it won't be any other list at the bottom part that is the 4 level. If this part of a node is not enough to hold the data, then it will eventually restructure. Then it will become a 4 level. But only until it won't be able to hold the data, then only it will restructure. So for the restructure part, it will take a lot of this overhead. Means the recalculation to calculate every node, and we build the tree again. So a leaf node has between n minus 1. So let's say we have each of these nodes have a 6 number on slot available, and 6 minus 1 equal to 5 divided by 2, and equal to 2 by 5. So it should be 2 and 2 minus 1. So it's 1. Okay. So eventually here we only have a 3 slot available for each of the data. Okay. So special case here is if the root is not a leaf, it has at least 2 child. So if this root is not a leaf, then only a 2 child is available. Okay. So this one is the special case. If the root is a leaf, then if the root is a leaf of this, then there are no other nodes in the list. So this one is another special case. It can have between a 0 and n minus 1 value. So if this part it didn't have anything, then it have a 0 value inside. Yeah. Okay. So this one is the starting. When we build algorithm or a structure, we actually mentioned this rule and regulation clearly. So for the programming part of us, we need to write some. Okay. So continue. Basic description. So example of this B3 of this order, we have a 6 slots here. 1, 2, 3, 4, 5, and then the next one 1, 2, 3, 4, 5. Because we have n minus 1, so we only can have a 5 value. Another one is actually reserved point to another box. Okay. Okay, leave a note must have between a 3 and 5 value. So this is 3 and 5. Actually, I mentioned if we have a 5 value here, then it's good enough. If no, then the root won't build too many of the leaf. It will try to hold one leaf, second leaf, balance, try to hold only 3 to 5 of the value. So 3, if only 3, then the root is already enough. If more than 3, then it will start trying to break it down to the leaf type. Okay. So the last one here say root must have at least 2 children. So this root when starting build this, if we have more than this number and it try to build the leaf, then starting it will need to build 2 leaves. Okay, so 2 shells at the bottom here. Then just move all others value down. So only one is at the top. Then move all others to the bottom of the leaf. Okay, so this one is another example when the tree built up. We can see have a lot of this name here, and at the top of this root we only have one. So before that, any of this name is before m will be in the left hand side. Any of this name that is more than greater than m will be in the right hand side. So this one is the root node, and this one any of this level is the internal node. Those that didn't have any child will be the leaf node. And for the leaf node, it will actually hold all the data. So although this one is Mozart, but actually it didn't hold any data. It's just a whole point to another one and a point to another one. The actual data and the pointer is actually in the leaf part. Okay. So before m, this part do a pointer to this non-leaf node. Although we see the pointer is point to here, but actually it should be reading from the top, from the left hand side. So start from here, left to the right. So it should be reading is in here. So if we want to find something, let's say click, actually do the comparison. C, okay, is less than m, so it comes to this part. Compare E, C and E is actually C is less than E, so it comes to this part. Start reading from the left to the right. So C is greater than B. Okay, next C is same, but check continue. Then with the next one, okay, we get the number. Okay, so this one is reading and how is the structure built up. We'll go through one example, and hopefully you will see. It will be clear. It will be clear. Okay, this previously already mentioned B tree is actually a big topic. A few times of this final exam actually have a related topic asking about this B tree. So before we continue about talking about this B tree, we just show some example. So this one is some sample, and I also send the URL for you, so you can just try. So we took this random and any number, and this one is insert the value of this one to our B tree. So it's just continue doing the insert part. So you can see we starting we say we want the maximum degree to 3. So we only hold up to 3 maximum, but more than that, then we'll just try to break it down. Okay, so this one is the value, and if we continue doing the insertion, you can see how many level is that. Okay. Okay. So if I want to find some value, let's say 1655. Okay, you will just check. Okay, 1 is less than 8, then it will come to this left hand side. 1 is less than 6, so it will come down to this side. 1 is reading the first one, 1695. We found the value. So this one is the step by step how this actually works. We found another number, 2000. 2000 is not in it's not here, so it's element 2000 is not in the tree. Okay, so this one is the step by step. Okay, so we continue to insert a few more value. Okay, I think enough for this part. Then I will remove this random. You want to insert the specific value, so let's say 1. Okay. So we see that a little bit here. You can see we have the tree structure is already quite stable. I say stable. So you can see we have three non-leaf nodes here. And each of the non-leaf node actually hold 2 values. And until we insert another one, so just now we insert 3 here. Okay. And when we insert 3, this value seems like not be able to hold this 3 anymore. So 1, 2 is actually in one node, one leaf node. And when this 3 is inserted, it seems like we do not have enough space to hold this 3 anymore. So it should break it down. Okay, break it down and reconstruct this node again. So repeat this part. Initially it's 1 and 2, and when 3 want to insert into this node, it seems like you don't have any more space. So what we need to do is we need to break the leaf node and reconstruct again. Okay, reconstruct. So 1, 2, 3. You break it down already. So only 2 and 3 are put in one side, and 1 is here. So the reconstruct of this leaf node will also affect the non-leaf node as well. So previously the non-leaf node is starting pointing to this 1 and 2 is 0392. But after we insert 3 inside, the number change, and this non-leaf node is also changed. Okay, so it depends how many level need to do the changes. So if the level is in this part, even at the top here, we may need to change as well. Okay, so this one is the insert part, finding part, and now we want to do some kind of deleting. So the deleting of this is number 3 will also do the same thing like previously we see that. So we try to delete number 3. Okay, so we try to delete number 3, then this part is removing. Only if the structure become unbalanced, then only if we try to restructure this part of the node. So if other thing is okay, then we will just continue the node. Okay, so this one is the basic idea of how this B-tree, insert, finding, and deleting is working. Okay, so we continue the PowerPoint. Okay, so this time we already see the animation and whether insert or deleting, they try to do a balance. So how many level we have, and each node actually each non-leaf node actually hold how many number. Then how many leaf node is actually belongs to one node. We also have the structure. So if this part of node or leaf node too much, then it will eventually restructure this part. If it allow this kind of thing happen, then it will become an unbalanced tree. So this searching, this kind of this B-tree won't be work or because if we follow rule, then this kind of B-tree won't be happen. But if accidentally something goes wrong and this kind of a B-tree happen, then it become an unbalanced tree. When the searching part too many items too many level go through, then the speed of searching will become too slow. Okay, so this one is something that need to mention when we come to this B-tree. So keeping a little bit tree balance is important to guarantee that no node will be very high level. So if too high level means that the searching part will need to go down too many levels to search an item, then the speed will be too slow. So it requires many block accessing during a tree search. So too many level means too many blocks until the end. So it is not a good point. So if possible, the algorithm will try to restructure everything to make and won't let this thing happen. Okay, continue on to this part. Ki, the item that we want to search for. So this one is the Ki search key value. And the Pi is the pointing part. So if we have one value that want to search, then it will just do a compare to the one that we look for, the point, and move to the point along with the pointer. So P is the pointer. If we want to search something that belongs to this level, let's say just now we use a quick example. So it will do the comparison, move to this part, and C is actually smaller than E, and it will come to this part. Okay, so this is the pointer, and this one is the bucket of a report. So for leaf, for non-leaf node, the search key is in a node order. So the number here, B, C, C, E, E, G, is actually in order. So if you go through this audit, it actually how many number is actually. Okay. So for I equal to 1 until n minus 1, the pointer is actually put to the pointing and then to the actual space. L is the leaf node, and I less than J, and this search key value are less than or equal to LJ search key. So this part is pointing to the leaf. When we do the searching, although it starts from here to the end, this part will be faster compared to we search from one by one. Okay, so this one is the main point of using an index. So from the starting to the comparison, then we can come to the specific or more direct to the key that we look for. Okay, for a non-leaf node with an end pointer, so this one is the non-leaf node, and you will have an end pointer. So this before E, you will have a one pointer. After E, you have another pointer. After G, you have another pointer. Okay, so of course, this time we didn't have any node yet. If yes, then you may need to restructure again. So if the key here is less than K, then it will come to this side. If the key is greater than M, then it will come to this right hand side. Okay, then I continue doing the same thing during the comparison. See which side they should go. So this one is to the left hand side, and this one is to the right hand side. Until you find the leaf, then only it goes step by step, searching to the node here. So this one is some of the programming part, saying that how this searching is actually go through. So it starts with the root node. Doing the comparison with the key. If it is the root, then only this value is there. If it is not the root node, then it will start searching from the smallest search key value. So example is this one. If it is not the root node, then it starts searching from the beginning of the bucket here. Okay, then the next part, if the value exceeds, let's say we have a result here, and if the value that we want to search for is exactly the same, then we will just follow the pointer, and directly go to the specific value. If it is greater than or equal, if it is greater than, then it will go to this part. doing the checking again, compare. If it's still greater than, then it will just follow the pointer to the leaf. Eventually, we didn't see any matching here is not equal. That we see the greater. Okay, so greater than the value is greater than the key that we compare, then it will just continue move to the node to the leaf. So this one is repeating, doing the comparison until you find the leaf, and only it starts doing the checking one by one. Eventually, a leaf reach a leaf node. If the key is equal the key that we'll be looking for, then we will follow the pointer key to the desired record and go to the specific position that we actually are looking for. Okay, so we have one example here that we want to find this Kim, and K is actually less than M. Okay, so M is less than K, so we come to this part. So we find this one by one. K is greater than E, K is greater than G. So we will follow the pointer to the bottom. Then since this one is the leaf node, we will do comparison one by one, and eventually we find Kim. Okay, so this one is how we're going to find a key inside this B tree. Okay, now continue. We have this update about this B tree. Let's say insertion, or let's say we have another one that is called deletion. Okay, so insert. We find the leaf node in which the search key value would appear. So we actually for insertion, we also still follow the previous one, searching for the key and see whether there is enough space or not. So if it have a space to insert, then we will just go to that part. So the first few part is still the same. We find the correct position. If the search key value is already there, then the leaf node record is at the top, and if necessary, the pointer insert into a bucket. So if the key that we want to insert is already inside the tree, then we just follow the pointer. Okay, so it is possible that the key that we want to insert is already active, then we just follow the key to the point. If the key that we want to insert doesn't exist in the B tree, then we need to do some kind of searching and then restructure the bucket. So if the search key value is not there, then we add the record to the main file. So we have this keyword here, main file, inside the correct place, that's pointing to the correct place. We create the bucket if necessary, then continue on this two parts. If there is a room, means if we have a space here, then we have a room, then we just insert the key there. But if there is no room, then we need to split and insert. So previously we have just now the B tree here, we have an example. We try to insert. Okay, we insert 3 inside. Currently we only have 1 and 2. We insert 3 inside, and the room is not enough to hold this value, so it needs to split and restructure this part. Okay, so this one is when the room is not available, then we need to do this split and insert part. Okay, so this one is splitting the list. We take all the numbers together. So just now we have 1, 2, and 3. We move it up from the list node restructure. We place the first n divided by 2 in the original node, and then the rest in the new node. Okay, so let the new node be key, then let this k be the list key value in key. So this one is saying the restructure of the 1, 2, and 3, seeing which one is that. So if the parent is full, if the parent here is full, then we may even need to restructure this part as well. Okay, so this one break it down, then restructure the previous one as well. So splitting of the node process upward to the node that is not full. So if you continue moving up, doing the restructure part until the root, we may even need to change the node if the tree becomes unbalanced. So in the worst case, the root node may be split. So currently our root node is only one number. So if the root node is also full, then we may need to split this root node, and eventually the whole structure the whole tree needs to restructure. Okay, so this one is because the number that we insert or we delete, we do not actually know which one will be. So the root node that we select or the program select is actually try to balance the left and right hand leaf. Okay, continue on. We have an example here that we want to insert Adam. So this is the original tree, and when we want to insert the Adam, it should be inserted here. So you can see we continue on searching Adam where should be inserted, and eventually we can see this part Adam should be inserted here. And the part here is it also tells us for rank and until LA. Since if we want to insert here, then this part it actually didn't have enough space for us. So what we need to do is we need to break it down, collect all the nodes, then use this. Place the n, you place the first n divided by 2 in the original node. So 3 divided by 2. We place the 2 nodes here, and all others will be added back. Okay, so this one is the example of insert Adam. We have another example that insertion of a different lamp pot. Lamp pot is L is greater than M, so we will move insert it in the right hand side, and L is less than S, so it should be someplace here. Okay. M. Okay, so we have this one S, then come down to M. So insert in front of the L, insert in front. So insert in front, but this one we do not have enough space for this. So what we need to do is we restructure everything. So we collect before. I'm missing some. Okay, so you need to insert some place here, but eventually there is no room for data. So what you're trying to do is collect everything and split it into the first one, second one, third one. Of course, we need to insert the value here, Kim, the lamp pop. So Kim and the lamp pop will be in one place, and the next one will be Mozart and Son. Okay, so if it do not have enough space to insert, then it will collect all, and also the one after the current node combine together, make another node, then divide all the nodes evenly. Okay, so this one is the example of insertion of a lamp pop. Then the next one is deletion. Okay, we rest 5 minutes before you go to the plus one here. Okay, now we continue this part for deletion. So this time we already cover insertion, and this part I think that is the deletion. Some of the time, most of the time the record won't be deleted. Only in certain cases, let's say the customer is already not active, or the company is already closed, and we delete it from the database. Seldom. But for this deletion, we try to find the delete item first, doing the same thing like previously, and remove the item from the main file. So and from the bucket as well if it is there. So if some of these items, let's say this one is actually point to fine, but yeah, this one is actually a point have the pointing of this tab. But if the one that we want to remove is wool, then you won't affect this equivalent. But if the one that I want to remove is actually the node, then not only are we removing this one, we need to redistribute this one as well. if the node that before, the node that after this leaf is unbalanced, too less, then it may need to restructure as well. Okay, so this one is for deletion. We take out one example here. The example. Okay, so this one we need to delete. Okay, this is the actual place. Since we want to delete this, and this one will be too less to hold the key. Okay, so this one is removed. So we can just combine these three together. And since we want to combine these three together, which is what we call redistribute. So since this one is removed, this one needs to remove as well. And the starting key of this pointing will be here. Okay, so this one no longer there. And because of this pointing to this part, this may need to restruct as well. So eventually they try to break it into, bring it up and try to break it into two parts. So before that, go is actually going to go. So this one we're adding a move this go up, and this is bringing down to the non-list node. And before of this moza, we are pointing to go, and after this moza, you're actually pointing to this one. Okay, so this one is the part of the deletion. So you can discover that removing of one non-list node, it will eventually redistribute almost half part of the tree. Okay, so this one is another one, deletion of this and sign from the result of a previous example. And you can see the effect here. The leaf containing a sign and will become under full, and borrow a value team from the left sibling. So typically, the one that here is already removing, then this one become only one. So it needs to bring borrow a team from the previous one here. Okay, so this part is actually a restructuring this one. Okay, so this is a big topic, but also a very hard topic since this is not a programming part. But we need to understand the structure, how it actually for each of this insert, searching, insert, deletion. Actually, the whole structure is moving. If there's too many items in one node, then we need to split and reallocate. If it is too less, then we need to combine and divide the item evenly to the other node. Okay, so this one is for programming. This one is interesting, but for database, since it's too many. Okay, so we already touch 2, okay, touch 2 this B3. Then we continue to this hash index. Okay, last chapter we already have this hash index, and we understand what is the reason why we want to use a hash index. And I already use Java as an example. Let's say we want to look for the main city of UK, then we can simply get London. Same thing about this hash index here. We use this search key and go through some kind of hash function. So normally this hash function is using a modulus by some value, and this value somehow is hard to decide. So some of the forum actually I mentioned, if we use some common or low value of this hash key, then actually it will eventually point to the same data bucket. So too many pointing to same data bucket, then it will actually full of a bucket. Okay, so today we will just go through some of the reasons why it become a full bucket and how to solve this problem. So hash can be used not only for the file organization. So let's say for your Windows system, you have this FAT32 or FAT16, then NTFS. This kind of file organization, we can also use this hash index, then we can find the location much more faster. But for database, we also can do it the same thing, because the data that's set into your computer system is actually the same method. But we want to find a specific location. Let's say for my name, I'm typing the data. Where is the data that's set in this? We want to find it much more faster rather than search it one by one. Okay, so this one is using the search key, then we directly go to the bucket that is indicated. Okay, so we have this hash index. Hash function find the bucket, then this bucket will eventually point to the file location. Okay, so we can find this record much more faster. So we have this static hash, and you can see the step by step here. And this one is the bucket, and you can see we have only this number of a bucket. Let's say we have a number of 8, 0 until 7. We have this number of 8. So all the value here will be both modulus by 8. What is the value? If the value is 0, then we place the number here. Okay, we place the number here, then we point to the specific location. So we can see if we have too many record of pointing to bucket 0, then it will eventually cause this thing called bucket overflow. Okay, so this bucket overflow or problem can be happen because we didn't have enough bucket for all the records. So you can see we only have 8 buckets here. So for one computer system, it won't be possible only have 8 buckets to save all the file or save all the hash key location. So this is one problem. Another problem is that it may fill into one part. So if we have a lot of record that if I'm using a modular of 8 pointing to bucket 0, then we may have few more record here, then it become bucket overflow. But actually, all other bucket is still healthy, so no problem. So this is what we call fill in the distribution of the record. The next one here, multiple record have a same search key. So we have a lot of record. The search key is the same. A lot of times when we let's say when we register a username, the first name, last name. In this world, actually we have a lot of name that is same. So it is possible that if eventually I point to the same part, then it will become a problem. Okay, so this is the problem of choosing this hash function, and we produce this non-uniform distribute of key value. So this is a non-uniform. If the the hash function is healthy. I say we use the word healthy or correct, then it will eventually distribute. Okay, so this one we have a 5 value, this the second bucket we have 5 value, the third bucket we have over. If everything is in sequence, in correct order, then good. If all the value point to 0, then eventually this bucket 0 will be overflow. Okay, so this one is the problem. Then we try. We know there is a problem of this bucket overflow. Then how are we going to solve this problem? We can handle by using it can handle this overflow bucket using this linked list. So if we have a lot of this pointing to bucket 1, then it will continue pointing to the next list. So if we have this problem, then eventually it means if previously when we point to bucket 0, we can directly get the location. But since there is too many items in the bucket 1, we need to go and search one by one. And maybe we have a lot of these buckets here, then the speed will be slow. So this one is the deficiency of the specific hash. When the database grows, the performance will degrade. So this one is understandable. When the database need to hold billions or billions of records, then of course the speed will, when we do the searching, insert or whatever, the speed will become a little bit slow. Okay, so the performance will be degrade due to too much of this overflow. So if too many overflow here, then it will take, let's say, 1 millisecond, and it may take many milliseconds to get the value from this overflow bucket. Okay, if a space is allocated for a display to grow, a significant amount of space will be raised initially. So previously, if we only if for this case we only assign add bucket here, some suggest that why not we just assign a big amount of a bucket, then it won't have this bucket overflow. But due to the calculation, if we assign too many, then of course it is a waste. So if the space we try to allocate the bucket amount is too much, then initially then it is actually the wasting. So how many number of buckets we want to assign initially is a big problem. So eventually we have this thing called dynamic. The next one here is when the database stream, normally it won't happen unless your company, the company sales or this customer all gone already, and no more data is inserted, and a lot of this data is actually deleted, then only it will come to this. So the space will be raised again. So we have another suggestion. So static is not a good one. When we didn't assign enough a bucket, then it will have a bucket overflow. If we assign too many a bucket, then initially it is wasting. If we stream the database, it is also wasting. So we come to the second suggestion here: dynamic versus static versus dynamic. So this one a common exam question. What is the difference between these two, and why we want to have a dynamic? Why we don't just use static? So it allows the hash function to be modified dynamically. So the hash function previously we say divide by 8. We use any kind of method to look for the key. Is based on the key, we use this hash function to find the bucket easily. So we suggest another method, say dynamic hashing, and this hashing it allows us to modify this hash function. So previously is divide by 8. Maybe we can just change it modulus by 16 or even a modulus by 32. Okay, so this one is a sample. So extent of this extendable hashing previously from 8 to 16, then it's extendable. If 8 is not enough, then we extend it to 16. Okay, so this one is possible. Hashing a function and generate value over a large range, typically 32 bits. So this is 32 bits. 2 to the power of 32 is equivalent to almost 4 billion. Okay, so it should have enough space if the company business grows dynamically, and it needs a lot of this bucket to hold all the data. Then the hash function can change to the power of 32. Okay, so the number of bucket also changes dynamically if it is needed when the system will discover if the system using this dynamic hashing, and if the record of this bucket all full, then it will change this hash function from 8 to 16 dynamically. Okay, so let the length of this say bi. So this one bi, the bucket address table size initially is I is equal to 0. Okay, so you can see we only have a few buckets here. Now let's say we have an example. So the value of this I will grow and swing depend on the size of this database. Whether it grows, then the I will grow. If the database swing, then the value of I will swing. Okay, so actually the number of this bucket is to the power of I. So this is the value. The number of a bucket also change dynamically. This part, how many buckets we need, it will just decide. Okay, so this one is some picture of some picture of this extendable hash structure. So if we have this hash prefix here, then it will point see which one. Okay, actually we have this function here. Then see which one actually point to. So if one bucket is already full, then it will eventually create another one, copy the whole thing, and break some part. Copy the whole thing and break some part to the next one. Although we see all the buckets, it seems like linked together, but it actually it's assigned into different memory parts. So we can just simply add another one in our memory, so it won't cost a lot. Okay, so extendable hash structure to locate that this bucket contains a search key. We try to compute. So this one, the calculation based on some calculation, we find the location and use the first I, the number of order. So we try to display into the bucket address table and follow the pointer to the appropriate bucket. So we use the hash key here, try to find the value, or if it is here, then we try to get the correct position, and we locate the actual record or actual file. Okay, to insert the record with the search key value k, doing the same thing, we check from the hash key, see whether there is anything. So if there is something, same thing, like what we say previously, the bucket overflow. We point to the same place. If the record is already there, then we just use the same key point to the specific location. If the record is not there, then we'll need to insert the key to the bucket point to the main one. Okay, so this one, it depends whether the room is available or not. If the room is available, of course, it's easy. If the room is not available, then we may need to divide this bucket. Just like I already mentioned, we may need to divide this, create another bucket, and move some part of the record here, and others remain in the same bucket. Okay, so to split the bucket J when inserting a record with the search key value K. So this one is computing programming again. Okay, so we have two case here. The first case here, we have more than one pointer to the bucket, and the second one, we have only one pointer to the bucket. So we clear. Okay, so you can see we have two pointers to the same bucket. If this is the case, clear this. Okay, so when you want to insert something and it seems like it's already full, and we have a few pointer point to the same bucket. What you're trying to do is we create another bucket. Okay, so let's say this bucket is Z, and we try to copy everything. Update the second half of this bucket address table to Z, and copy the whole thing to Z as well. So this part will eventually point to the Z part. Remove all the data here from the bucket J, and reinsert again. So we remove everything and reinsert again. Cut half of this and only place them here. So this one is the static and move the second half of the pointer here. Okay, so it will eventually separate the pointing of the first one and second one, but we still keep all the record, but the record is splitting into two buckets. Okay, so this one is if the pointing is more than one, then this is the case. If the pointer is only one, then if the pointer is only one, so we take this one as an example. The pointer is only one, and this is already reached the limit, and too many splits have happened in this instruction, so we create an overflow of the bucket. So this one we give the warning of this overflow of bucket. Okay, so increment of this I and double the size of the bucket address is needed. So we double the size of this bucket. Replace the each of the entry in the table by two entries that point to the same bucket. We compute new bucket. Okay. So we have this 10 only a point to this part. If too many of insert into this bucket, we try to increase I, and we also create another bucket. So copy everything from this bucket to the second part, and pointing the new I to the new created bucket. After copying or duplicate of this, we do the compute again. See whether this one pointing to which part, and any of these items which is not needed can be removed. So eventually both of these will have a half part of the record, and the bucket is not overflow. Okay, so this one is the programming part that I mentioned. If it is overflow, then how are we going to solve this problem? Okay, so next one we have this deletion. This one deletion is a little bit easy from others, but it is trying to sync this. So if some part of this record is actually not needed, and the bucket is not even hold any data, it can be eventually this bucket is removed, and the linking of this is removed as well. If the value of this hold two less of data, then eventually it can just combine two buckets of data we calculate relinking of this hash prefix. Okay, so this one is simple compared to the instruction. Too many things happen in one time. Too many data into one overflow bucket, and we need to settle a lot for this case. Okay, so this one is for deletion, and this one is the example. Initially, we only have 0 of data in the bucket address. And continue when some of the data is inserted, how this can happen. Okay, so we insert Mozart here, and Sinivasan here, Wu here, and continue. So based on a different value, we insert into different this bucket. Okay, so you can see the bucket is actually a continuous increase, and the hash prefix also increase. So based on the value that I need to modulus by what number, it can be just continuous changing. Okay, so the hash prefix is also changing. So previously we say extendable hash structure. The hash prefix is keep changing from the 2 to the power of 0 to the power of 1 to the power of 2. So this hash prefix is changed. Previously it's 0, and now say we say 1, 2. So when this hash prefix is quick, we do not need to hold so many data. So the starting is 0, and when the record keep increasing, so the hash prefix is changing as well. So this is the characteristic of extendable hash structure. So you can see when the record keep increase, the hash change as well. Okay, so the hash now change to 3. So we finish this hash structure, extendable hash structure. Then we just do some conclusion of using this index. So the rule of using this index, we know previously we already mentioned for index, it's actually a burden to the database structure or to the computer system as well. When we keep changing the data, if we have a lot of data deletion and updating of the data, the index calculation is actually run in the background, and it will cause this overhead burdens to the system. So it's only used for large tables. Okay, so if we do not have a large number of records, then we do not need to use index. So it's used on a large table, and we have one rule here. Advice when there is more than 100 value, then we use index. If less than 30, we can search the computer system can search the value easily, so we do not need to do indexing. So index normally apply to primary key of each table. So when we try to search something, it actually good to put the index for the primary key. So if we search ID, it will be much more faster. So normally it's already sorted. The index search field normally is in the way concept, so where ID equal to 1001. So this one is the search key. Field in SQL order by or group by as well. So we have one way here. We also have another one order by. We also have a group by. Normally, if the user put this field in these 3 parts, normally this will be using the index. Okay. So another field rule here: avoid use the index for field with a long value. So this is a long value. I have experience here. If the user wants to search address, and the address like Batu Gajah, and it is a long word, Batu Gajah. So in front put a percentage. So if the address have this Batu Gajah, then we want to get. So this is some kind of what we call a long value for the field. The address is somehow very long. If you didn't break the address into few parts, Jalan, Taman, city, state, country, then eventually if you combine all this together, become only one address. And if this address you want to search something, let's say Batu Gajah, then it will take a very long time. So this is not a good practice when you are indexing. Okay, so DBNS may have a limit on the number of index per table. So we actually do not know how many number is that, and it is different from one DBNS to another. So previously I heard we have a MySQL, MS SQL, Oracle, and we have some more that is free. The setting is all different. Okay, so there is a different limit on the number of index. So we don't know until we face the problem, then only we know. Okay, so be careful of index attribute with a num value. So for some of the DBNS, they actually do not know how to compare this num value, and many of the DBNS will not recognize this keyword as well. So for the index search, so if this happens, means that eventually you will find a new record. Okay, so comparison the index technique, we try to consider is the cost of prioritize. So we try to reorganize the index whether it's acceptable. We always have this thing. If you try to delete, if the company system always try to delete, update some of the field, then it actually is the cost. A relative frequency of insertion and deletion. Check we don't know until we find that our whole computer, whole DBNS, the speed of our DBNS becomes very slow until it may hang. Then you have to know. Okay, so a lot of companies actually employ one system administrator, employ one database administrator, and they will work together. So like my previous company, they actually employ these two, and they keep track of the computer system performance every day. Look at the monitor, and if the process is somehow greater than 70 or 80, then they will issue a warning to each of the employees saying that stop your behavior. What is your activity? Please report to me immediately. And it is their job, and hopefully the server will now, the database won't crash, and the performance is still there. Okay, so it is a driver to optimize the average access time. The main point of this indexing is actually access time, how fast you can get the result, but also it will bring the whole computer system some kind of overhead. So previously we mentioned if you want to restructure updating of this indexing, it takes a lot of resources. Okay, so this one worst case, best case, average case, whatever, it's actually good and bad for the computer system. So aspect type of a theory, we try to say hashing is generally better at retrieving the record. So we have a lot of number, and having a specific value. So a specific value means equality. So if you want to search something, say mean equal to time sizing. So this one is a specific value, but it is not good for range search. So if a salary greater than 10,000 every month, then this kind of a good using this B3 index. Okay, so based on the different kind of searching, then we use a different kind of indexing. Okay, so the computer, the DBS must able to differentiate these two. Okay, so this one is some example, and the last part here we have the database tuning. So when your car already working for running for some time, then you may need to do some tuning. So this is the index tuning. The goal is to evaluate dynamically evaluate the performance as a requirement and recognize whether any of the index yield the best performance. So if the index didn't use for some time, means that if nobody is using that index, then you may eventually remove that one. If the index, a lot of people using that index, but it causes the computers into trouble, a lot of the problems, then you may eventually need to reorganize the index. The reason for the revisit revising the initial index choice. So which field you want to index, we always the DBA will always need to consider. See if a lot of people are searching for the item, then they try to index it. So certain query may take too long time to run due to lack of an index. So if you didn't index that table, then too many users eventually search the same thing, then the DBS may down. So the index may not get utilized. So they have a one chart for that part, whether this index is actually used. So the index may undergo too much of an update. You index it, but they keep changing. So the server may from time to time need to do the updating again and again. So based on the attribute that undergoes a frequent change. So if you change your address so many times, then of course you won't use the address as an index. Okay, so this one is the reference. I thought I can finish 5 to 10 minutes before it ends, but so eventually I finished at this part, but I still have a problem. Okay, any problem regarding assignments again? We try to clarify everything before we end our class.